Let's now talk about the long-waiting special kinds of functions: injection, surjection, and bijection. And we're going to talk about each one of them by, first of all, introducing their formal definition, and then we're going to give you a series of examples to really consider. Actually, I should really say either example or counterexample. Those examples that do not belong to the category, for example, for injection, is also worth your attention. You should really know why a particular function will fit into one category or not. Right, let's now start with injection. So given the function, either partial or total, we're going to learn about for each of the three kinds that we're going to speak about, they can either be partial or total, right? Oh, maybe one thing I can just illustrate very quickly. So there are actually two dimensions that we want to consider, which let me just show to you. Okay, you can think about whenever you actually got functions for you to fit in its properties. One dimension is about either being partial or total. Okay. Another dimension is whether it's injective or surjective or bijective. So that's what I meant by two dimensions for you to think about. So what I highlight in orange is simply just one dimension. What I highlight in green is just the second dimension. So whenever you want to think about one function that's given, whether it should be here or maybe here, or whether it should be here or over here, that's something you have to decide, right? So each one of them is actually going to be something you're going to consider. So we got 1, 2, 3, 4, 5, 6 possibilities, and we're going to see each one of them as we go through the rest of this current video. All right, just to make sure you understand about two possible dimensions for categorizing functions. And of course, again, you should also understand another dimension, whether a given set of pairs is really a relation or is a function, right? There's another dimension, but let's not bother putting that on the paper in this case. All right, let's now talk about examples. Actually, definition first. If a function is injective or one-to-one or an injection, so either of these terms can be interchanged. So you can see, you can say any one of them. I believe most of you may have actually seen this saying maybe more often in the earlier math course, but in this course, you definitely have to make sure you know each one of them. Again, F can be set to be injective, or can be one-to-one, or it might be just an injection. Okay, if the function does not actually map more than one members of the first set S, well, we're talking about the relation between S and T, into a single member of T. So it is not allowed to actually map more than one members into the same member. That's basically how you should really remember it informally. Let's see the formal definition. Okay, we'll say F is actually injective if and only if, and we're using universal quantification to actually specify it. So we talk about S1, S2, and T such that, so this part here is the typing constraint. So we say S1 is from the first set, S2 is from the first set, and also T is from the second set. And we're talking about the relation between S and T, of course, as always. And this is the property that an injective function should really satisfy. If S1T and also S2T, if these are the two member order pairs in the function, in that case, S1 must be equal to S2. What does that mean? You can see here, S1 and S2 over here. So these two, actually, let me put it this way. That should be the right way to put it. So if you see T here and T here, apparently T is equal to T. If somehow you want to map to the same value T, in that case, the only way that's possible is you actually map from the same value over here. So that means it cannot be the case that S1 and S2 are actually different. You cannot really map from different values into the same value. Okay, that's also what the formal definition is saying. Let's see example together. All right, and what I will do is I'm going to go over a series of examples together with you on the iPad, and you definitely can see the more concise answers in the slides. Let's take a look. All right, let's now move on to injective. Okay, and what you really want to notice in the formal definition for injective function is to see when the value that's being mapped to is the same. In that case, the domain value must be the same, right? You can definitely also try to interpret that differently using contrapositive, like what we did for the functional property. I'll leave that exercise to you. If you got any trouble with that, you can let me know. All right, let's now see examples over here. Just about the syntax. If you want to talk about injection, it can be either, well, afterward is a partial, well, there's a one dimension to see is an injection, but the other dimension should it be partial or total, right? That's a difference over there, right? Either, so here we say this is the set of all possible partial injections between two sets, and this is the set of all possible total injections between two sets, right? And the way to write it, let me just repeat it over here just to show you how you can write it. To start with, let's recall how you can write partial function versus total function. So this is how you write a partial function, right, from before. And this is how you write a total function over here. But now, if you want to add a second dimension to say the partial or total function is also an injection. Injection is really about when you actually got two distinct domain values, they cannot map to the same range value. That's really the essence for the injective property. So that's why always remember, whenever you want to judge whether or not a function is injective, you always have to look at the domain values to see if the two different domain values will map to the same range value. So domain is going to be adding two distinct domain values over here. So the tail over here, this part over here, think about it's more like a domain. Okay, so that's the essence, right? Just remember, that's how I remember it, at least, just to share with you. All right, similarly, the tail over here. This is partial injection. This is total injection. All right, the symbol is also very important, right? You can also see the ASCII characters representation in the slide as well. I'm going to let you read it. All right, let's now talk about different categories one by one. All right. So what? Let me start with. Let me be careful since we got so many things. So focus on one example at a time. All right. The first one, and you can see I'm using a subset relation again, right? That means I'm giving you multiple examples, right? Over here. The first one, empty set. Empty set is actually okay. Let me do it. Empty set is actually actually a partial injection, right? Why? Okay. Let me start with the empty set. Over here, first of all, it must be partial. It cannot be total. Why? Well, if it is total, then that would mean you have to have the domain being exactly equal to 1, 2, and 3. But the empty set contains nothing, the empty relation or empty function. All right. First of all, so it's definitely partial. But what about injection? Why is empty relation? Why is empty a function also injective? Well, it's a similar arguments, right? It's a similar argument as we said before about why the empty, let me just go to that particular page just to remind you over here, right? We said before, the smallest function is the empty relation. And the reason is that we cannot find any witnesses in the relation to disprove the functional property. So now we got a similar idea over here, okay? So the empty set over here, it's also injective. Number one, not total, and number two, it is injective. Because, let me write a little bit more briefly. No witnesses of violation of, right? So you definitely have to make sure you understood what we said earlier about how you can prove or disprove universal quantification. So here we got universal quantification and also we got implication, right? Over here, right? So this is the first example just to show. So empty relation is a very special empty function, right? When I say empty function, empty relation, I really meant the same thing. So empty function over here is simply both partial and also injective. Okay, let's see the second example. And be careful when you're reading the second example here. You can see there's a comma over here. There's a comma over here. So we got 3 examples in total to show to you, right? Be careful. Okay. So the second one we're going to look at will be this one over here. Okay, be careful. So this one, only this one, is a function being a set of a single pair. Okay, is this injective? Well, according to the definition over here, if you actually got 2 pairs, in which case you got T the same, but we only got 1 pair. So that means the antecedent is already false. False implies anything. So this will just be satisfied automatically. Or thinking this way, you cannot find any two pairs where the second elements are the same, but somehow the first elements are different. In that case, you will find a violation. But you just don't have the you only got one pair, so it's a special case where the antecedent will just be false. All right. Let's see the third example. The third example is over here. We got two pairs over here, and in this case, can we find any two pairs where the second elements are the same, T and T? No, A and B are simply distinct. In that case, we're okay. So we got also the antecedents actually false. In that case, false implies anything. Right? So far we have seen 1, 2, and 3. All of them are the partial injections between these two sets over here, and that's why we're using a subset. So this is a member of this set of functions. This is a member of that. This is also a member of that, right? It's something you should the convention we have been using for the example. Let's look at the next one. Okay, the next one. Let me use a different color over here. How about that? So this is the single function that we are looking at. This one over here, right? Is this a partial injection? Okay. First of all, is it partial? It is partial because if you look at the domain values 1, 2, and 3, which is a subset of 1, 2, 3, which is good. And what about the range value? You can see we got duplicates over here, B and B. So we got T and T over here. And then we got S1, S2 being 1 and 3. 1 and 3 are not equal to each other, whereas the property required them to be equal. So there's a violation over here, right? So you can definitely see that over here. For this particular example over here, what you can just try to annotate a little bit. Let me do it over here. So what we can do is B is equal to B implies, according to the property over here, that 1 should be equal to 3. But this will just be false. Because we know that 1 is equal to 3 is going to be false. So we actually got true implies false. So that'll be a violation for the property, right? You can see B. Let me just try to be even more explicit over here so you can see the two pairs, right? But it's really important to get the basics completely understood. So you will be able to do more advanced examples on your own in the test or in the exam. All right, so this is not a partial function. That's why I said it's not a member of, right? That's the obvious operator to use. It's not a partial injection. Okay, to be more precise, it is partial but not injective. Okay, that's also something you will see in the slides. So this function over here actually is partial but not. I don't need to say but not injective. All right, let's now look at the last one for partial injection. Let's now try to use this one here. Let's say that's another function, the pink one we're looking at. Similar, you can see here we got B and it's a partial 1 and 3, which is a subset of this domain, this first set from which we build the function. And then we got B and B, similar arguments over here. You can see B and B, T and T, which requires the corresponding S1 and S2 to be the same. But now 1 and 3, they are not the same. So there's a violation for the property, right? For the same reason that how we argue. So I'm gonna let you make the notes if you want to. So that's why it's not a partial function between these two sets. All right. So hopefully now you got a better idea about the partial injection. But I think always keep in mind we got this particular table over here for you to think about how to categorize the functions. You got two dimensions, right? Being injective, surjective, or bijective, or being partial or total, something like that. All right. All right. Let's now take a look at total injection. Now we are requiring that the function must be number 1 total and number 2 injective. Right. Let's now take a look. And the first one is kind of interesting. Okay. Look at this equality over here. I'm saying that if this will be the set of all possible total injection. So let me just write down. So what this symbol over here really means is the set of all possible injections, total injection to be more precise. And let's over here to highlight a bit. So set of all possible total injections that you can build from the two sets 1, 2, 3 and also AB, right? I'm claiming that this will just be empty over here. But why? Okay, thinking this way. If you really want, think about how you may construct such set, right? Think about how you may construct it over here. Let's start with that. If you want to, it's going to be total, which means 1 should be here, and also 2 should be there, and also 3 should be there. So this is to satisfy the first criterion where it must be total. And now how do we fill in the second elements over here? How many choices do we have? Well, basically we can choose only A or B. So let me say and we know that it must be different elements. Let me just say this: different elements of the domain value must be mapped to unique values in the range, right? So now, in the interest of that, let me simply just try to say I put A here and B here just to be unique. But now in the third one, doesn't matter what I choose. If I choose A, it will make it non-injective. If I choose B, it will also make it non-injective, because over here, if I make it A, these two pairs will be the witness where the injective property is violated for the same reason that we argued earlier, right? That's a very important, kind of interesting property to actually see, right? So what I'm saying is, I'm not saying that the empty relation is a partial. I'm not saying that the empty function is actually a total injection. That's not what I'm trying to say over here. I'm trying to say that there is simply no possible function that's total and also injective from these two sets. That's what I'm trying to say. Okay, so it's really make sure you understand exactly what this empty function over here. Let me say it again, or you can rewind. I'm saying that there is simply no possible way to build a total function that's also injective between these two sets. So that's why it's empty. So the set will just be empty, meaning that nothing can be there, right? And that's exactly the rationale behind. All right, let's now take a look at the next one. And let me highlight it, this one over here. Okay, so this seems to be a total relation. Let's see, let's check the both dimensions. What about total? 2 here, 1 here, and 3 here, which is exactly the same set as the first set from which we built the function, right? So that's total for sure. What about injective? Well, since there is no duplicates of the range value over here in the second element, so in that case, we actually simply got this antecedents false. So false implies anything, so that'll be satisfied. All right. So this one here, the green one, let me just make sure it's green. So the green one over here is actually total. Actually, I don't need to. It's both total and injective. That's why it's a member of. All right. Hopefully, so far so good. Let's now take a look at maybe some counter examples. Okay. The next one, let me use pink. Let's say this function over here. Okay, over here. First of all, is it total? Let's be careful. Is it total? You can see here we got domain value is simply 2 and also 1, which is only a proper subset of the first set. It's not equal to, so it's not total. Okay, first of all. Okay, you can see this particular one over here. Let me make a note right away. It is total. Okay, is it injective though? It will be injective because you can see there's no duplicate of the range value. We only got C and D. So the antecedents again over here is simply false. False implies anything, right? So it is total, but not injective. Right? It's really important for you to see which dimension might be satisfied. Maybe one of them, or maybe both of them. All right. The final example I would like to talk about is over here. Let's use orange. What about this function over here? Again, let's decide 2 dimensions. Let's start with the total function property. Is it total? Well, you can see 2 here, 1 here, and also 3 here, which is exactly equal to the first set. So definitely it is total. Okay, I just noticed that I wrote the wrong comments, which I think my explanation was right actually about this. I meant to say over here, not total but injective. I beg your pardon. Okay, not total but injective, right? Not total because 2 and 1 is only a proper subset, not a subset. And also injective because we got unique elements over here for the range, right? It's total but it's not total but injective. I'm pretty sure my explanation earlier was actually right. I just wrote the wrong thing. It's a conclusion, okay? All right, let's now continue with this. Okay, this one for sure it is total because we got 2, 3, 1, which is equal to this. Is it injective? Well, no, because you can see D and D over here, T and T, meaning that the corresponding domain value S1 and S2 must be equal if it has to be injective. But in this case, 2 and 3, they are not the same, right? Let me just write this down again. But not injective. If you were ever asked to really justify, that's something you have to know what to write, right? In this case, for example, you can look at these two pairs, 2D and also 3D, right? You can say 2D and also 3D, right? In this case, D is equal to D for sure, implies 2 is equal to 3. This whole thing, this whole implication will actually will evaluate to actually false, meaning that it actually violates the injective property. That's why this is not injective over here, right? Because when these two are the same, that means the domain values over here must be the same. But in this case, 2 and 3 are not the same. All right. Okay, so that's about a very thorough discussion of the injective functions. Hopefully it makes sense to you. And you can definitely go through the slides. The only thing I didn't really point out to you is about the Ascii syntax for the partial injection. For example, over here, you can, again, the plus over here is to really make it like a mimic the visualization of this part over here. I'll let you study that, right? And this part is the tell. And also we got the ASCII characters for total injection over here, right? You can see there's no plus. And we also got the tell. All right, let's now move on to the next special function, surjection.